Hello class, so this is CSE 5250, Section 1, Week 6, Spring 2023. I have the syllabus opened up right now to look through what we're supposed to be doing up until spring break. So here's the plan. Right now we have our next assignment, which is to write a matrix multiplication program using OpenMP. It's going to build off of the dot product program that we wrote in the previous programming assignment. We're basically just gonna copy that code, stuff that in a for loop, and then stuff that in another for loop. So we have nested for loops, and the innermost for loop is the dot product calculation from before. We're going to parallelize one of the for loops. I described this in one of the previous videos. So that way we can, in theory, have multiple dot product calculations happening at the same time. I also have an example of trying to brute force the Pythagorean triples and changing it slightly so we can see whether we can find solutions to a modified Pythagorean theorem. Really, all this is to get you primed up for how we can parallelize the set of Eratosthenes, because this is going to be our big main assignments for the entire course. Writing a program that finds prime numbers. But the whole point is not to find prime number finding programs. It's really to find out whether we can make it parallelized and whether we have a worthwhile speed up. So, with that out of the way, what I will advise is, alongside your matrix multiplication program, start looking at how you can write not only the set of Eratosthenes, but how we can parallelize the set of Eratosthenes. Later on, I'll be talking about how are we supposed to benchmark this. I'll give you some guides on how to do that. I already talked about how we can use, for example, the chrono library to find the execution time of a program. Anyway, we're gonna skip ahead a bit and talk about a little bit of theory and a little bit of application. So, let's start with some theory. We have various theories and models for describing sequential computation. Of course, the star of the show is going to be the Turing machine, specifically the universal Turing machine. But really, if you have a Turing machine simulated on anything else, that something else is as powerful as a Turing machine. We say such a machine is equivalent to a Turing machine. Lambda calculus, we can simulate a Turing machine on a lambda calculus and declare that to be Turing equivalent. Von Neumann architecture, that's closer to what we have on our computers. It's often said that our computers are Turing machines. That's not quite true, but it's close enough. By that I mean, Turing machines are based on the Turing machines. Technically, they're supposed to have infinite memory, but put another way. But more specifically, they have infinitely expandable memory. So we can just so we can just expand the tape as much as we need to without any bound. Our computers have a limited amount of memory, so we can't really do that with our modern-day computers, but they're still pretty powerful as they are. So, for our purposes, we say that our computers are Turing machines, even with the memory restrictions. Anyway, that's enough. That's enough of this divergence. Anyway, generally speaking, if we can simulate a Turing machine on something else, we say that that something else is Turing equivalent. So, lambda calculus, Turing equivalent. Von Neumann architecture, also Turing equivalent. There are also esoteric examples of Turing completeness popping up in somewhat unexpected places. The Game of Life by the late great John Conway, Turing complete. You can simulate a Turing machine on that. Minecraft, Turing complete. You can simulate a Turing machine. You can build an entire Turing machine using pistons and redstone, and a tape that's pushed around by redstone block. By no, it's pushed around by pistons. You have a read-write head that reads the tape, swaps some blocks on the tape to write a different symbol on the tape. The pistons move it back and forth based on whatever program the Turing machine has. And because of that, we can say that Minecraft is Turing complete. But we can also build entire redstone computers in Minecraft. That starts going back into like digital logic and how you can build logic gates. And from there, you can package them into larger assemblages, like a 4-bit adder, memory cells, all that to build up an entire fully functional computer in Minecraft. And people have done this. There are all sorts of videos on YouTube talking about all sorts of redstone computers in Minecraft. And all of those would be Turing complete too. Could you run prices on it? Probably not. I think I broke that joke, but anyway. Magic the Gathering, also Turing complete. In fact, a paper called Magic the Gathering is Turing complete by Alex Churchill, Stella Biderman, and Austin Herrick. This paper is Turing complete. This paper actually describes a standard legacy deck, a 60-card deck that you can play, and what it does is simulate an entire Turing machine. Although some open world sandbox games such as Minecraft and Dwarf Fortress can support the construction of Turing machines, these Turing machines have no strategic relevance, and those games are deliberately designed to support large-scale simulation. Even this paper talks about Minecraft. The Turing completeness of Minecraft. So Turing completeness in weird locations. Minecraft is Turing complete, as I mentioned. Magic the Gathering is Turing complete, as I mentioned. This paper also gives you the entire deck list for the Magic the Gathering Turing machine. And here it is. The 60-card deck list to simulate an entire Turing machine. Not only does it describe the cards, this paper describes what those cards are doing. So there, if you ever wanted to go to your LGS and get these cards, just so you can make your own Turing machine in Magic the Gathering, here's the deck list. Speaking of other esoteric examples of Turing completeness, someone made an entire Turing machine in PowerPoint. So, another esoteric example of Turing completeness. What do we have for parallel computing, though? We don't have anything as universal for a Turing machine, it turns out. But we do have various models for describing different modes of execution. So, before I get into that, how would we even write parallel code? Well, one way is to have the compiler do some of the work for us. We could conceptualize of, say, an AI-powered compiler that can read the code and recognize sections of code that can be made parallel. So if we have, for example, 20 variables being declared one after the other, and they each have unique values that don't depend on other variables, we could just have the compiler compile that program in such a way that all 20 variables are declared all at once. Or what we can do is what we've been doing so far. We write a program with little bits of special code, compiler directives, that tell the compiler to do something else. that something else is basically to make a specific section of code parallelized. For our purposes, that was the parallel for loop, and to an extent, declaring critical sections. Because when you make something parallel, you introduce the hazard that is called race conditions. It's when one process races another process to try to write the same thing to the same place at the same time. And that's why it's called a race condition. They're kind of racing each other. But we don't want that to happen because if we don't want race conditions to happen because we might get garbled data that way. So we enforce synchronization, say one process at a time, to make sure that we don't have race conditions happening. It is okay if multiple processes read from the same section of memory at once. It's a problem when two processes try to write to the same place at once. So we can have the compiler do some of the work for us, or as another extreme, we can write it all out ourselves. We'll be doing this when we start looking at MPI. We'll be writing a parallelized for loop manually. The easiest example I can think of is to have an array have a program that reads an array and say it's going to do something with this array. One thread could read every even numbered indexed element in the array. The other one can read the odd numbered indices. So one process reads the even numbered indices, the other process reads the odd numbered indices. And that would be how it works. However, when we do the for loop, we can't have like something like I++. We can't have that. It would have to be, in our case, I plus equals 2. That way, one process always does the even numbered elements, the other process does the odd numbered elements. And that way, if you're to visualize this, you can imagine one process leapfrogging over another. The amount that we're leapfrogging, by the way, is called a stride. So we stride through the array, skipping some number of elements, but it's always going to be the same number of elements each time. And this can scale up no matter how many processes we have. So if we have 3 processes, we would be skipping. Each process would be doing something, but it would be skipping over to the next element 3 elements ahead. This is if we're reading, say, numbers in an array. Anyway, we're gonna look more into that when we start looking at MPI. So let's look at the models of distributed execution. The first one is called single instruction, single data. This is your standard sequential program, no parallelism whatsoever. In other words, we call it boring. This is probably every program you've ever written prior to taking this class. The next one is called single instruction, multiple data. Same instructions, different data. This is where our parallelized for loops fall under here. And this would only work if the for loop iterations, each iteration is independent of the previous one, so it doesn't have to. So if you skip ahead to if you do iteration 1, it does not affect the result of the next loop iteration. This is also the basis of GPU computing. So something like NVIDIA CUDA, we're also gonna look a little bit into CUDA. We might not be able to try it out for ourselves, but if you have an NVIDIA graphics card, I would encourage you to try it for yourself, though, because this is one of the more powerful this is one of the most powerful ways of writing parallel programs without having to resort to writing code that is to be run on multiple computers. That's what MPI is doing, by the way. MPI is not limited to creating processes that are all on the same computer. I'll talk a little bit more about this as well, but here's the idea. You may have learned in operating systems that there's two ways for processes to talk to one another, even though each process thinks it has the entire computer to itself. The first one is shared memory, pretty simple. Two processes have access to the same section of memory, and that's where that's how you get your race conditions, by the way. Another one is to send messages between processes that may be on separate computers. So that's what MPI is doing. That's how it's different from OpenMP. OpenMP is processes that are part of the same process. OpenMP is multi-threaded programs that are part of the same program. MPI is multiple processes that might not necessarily be on the same computer. We say it's on a network. So SIMD is more along the lines of NVIDIA CUDA, GPU programming a GPU to execute computer code in parallel. Multiple instructions, single data. Different code on the same data. So if you can imagine, you have an AI traversing a maze and it reaches a branching path. Say it has to go either left, right, or forward. So what do? What you could do is have the process fork into three separate processes and have each process take one of the three paths. One of them is eventually going to reach the end of the maze. The other two might get stuck in a dead end, or worse, loop back on themselves. Though, so one process goes another way. If this was all one process, that process would need to know how to backtrack to where it originally forked. It would have to backtrack to where it made that initial decision to go, say, right, and the right path terminated and it reached the end. It would have to go back to that position and then try a different path. Different code on the same data. Backtracking algorithms in parallel is the example here. MIMD is actually the most general of these different execution models. It can, in theory, simulate any of these. What came to mind when I was first taught this was a client-server model. So processes could come and go. Processes can come and go. They can do all sorts. They can read data. They can do their own thing. They might be communicating with other processes. If it's at the extreme, it's doing its own thing and not talking to any other process. That's one extreme. The other extreme is processes come and go, and some of them just form. Some of them are talking to one another, executing a parallelized for loop. So that's the four models of distributed execution. If you look this up online, you'll more or less find the same 5 models. There might be even a 6th model, but really this is what we're looking at right now. Okay, there's a 5th one. SPMD. Single program, multiple data. It turns out this one is a little bit more practical than just pure MIMD. Or pure SIMD. Single program, multiple data. A single program contains the code to perform different tasks. Copies of the program may perform just one task on the same dataset. This is also, this encompasses, this has overlap between SIMD and MIMD. This also includes something called task parallelism. So, what we were looking at so far was parallelized for loops. We could, in theory, have for loops doing something specific. So one thread does one thing, and another thread does something else entirely. We would do that by writing a for. We don't need a for loop. We need an if statement that says, if you are thread 0, do this other code instead of do this code that's different from all the other threads. This turns out to be more practical than, as I said, this turns out to be more practical than pure SIMD and pure MIMD. This is kind of what we're doing with OpenMP. We can have two threads doing their own thing independently in a C++ program that's multi-threaded. And that's how some programs are actually written. If you can imagine a video game where one thread is reading a MIDI file to play music, and another thread is listening to your network, sending and receiving stuff on a network, another thread is listening to player input, and another thread could be like doing stuff related to the physics engine. That is an example of task parallelism, where each thread has a different task to do. So, the examples of brute force. There are various examples of brute force, by the way. The Pythagorean theorem example that I gave you as part of your second programming assignment. As I said, there are ways of generating Pythagorean triples. Given values u and v, it will generate values a, b, and c. That is a valid Pythagorean triple. What we're doing is a little bit inefficient, but it is a good example of what's called brute force. By that, I mean brute force is basically trying out every possible thing in the hopes that you would solve a specific problem. An example of this is with finding the tallest possible cactus in Minecraft. So the video here is called The Quest for the Tallest Cactus in Minecraft. Watch this in your own time. It's a bit interesting. It also includes parallel programming. It's a combination of brute force and parallel programming that is used to solve a very, very specific problem. And given recent Minecraft updates, I don't think this will work in the latest version anymore because they changed the way terrain is generated. So this would only work on some of the older versions of Minecraft. So, whatever the tallest Minecraft cactus is now, I think you need I think you need to find a whole new set of seeds for that now. But either way, it's an interesting video. It's a neat application of parallel programming, even though it's a little more it's a little less practical than other things such as machine learning, but it's still fun. Anyway, if you want other examples of applying brute force to solve a specific problem, consider this thing here. If God had a Rubik's Cube, if God had a Rubik's Cube and he knew, and he was this, if God had a Rubik's Cube, what is the fewest number of moves needed to solve any scrambled Rubik's Cube. So, here's how it works. Oh no, it's scrambled. But I can unscramble it. That took 3 moves, so therefore God's number is at least 3. There's all sorts of... There is a video by a YouTuber by the name of JPerm, who talks about the interesting history of finding what God's number is. Spoiler alert, the number is 20. But it took like 30 years just to find that number. A naive and horribly inefficient way of finding what God's number is to do the following. So this thing, the Rubik's Cube, this is not a Rubik's brand Rubik's Cube, but anyway, there are 43 quintillion possible ways to arrange all the pieces on this thing. We can feed a computer all 43 quintillion scrambled states and have it try to solve every one of them, and we wait. If the highest, whatever the highest number of moves is needed to solve that is God's number. Of course, you have to find what is the optimal way of solving one of these things. So that is its whole that's like its entire subject in and of itself. How do you solve one of these things? And now it's scrambled. Anyway, you have to... Yeah, then, as I said, the naive way is to go through all 43 quintillion possible ways to scramble a Rubik's Cube, and to see what is the highest number of moves needed to solve all of them. So of course, if you're to just give this thing to a computer, it would take forever to run, like millions of years just to run the thing. And it could be worse. It could be even billions of years. So after 5 billion years from now, you're still waiting for your computer to solve a problem. What's God's number for this thing? You're gonna have to take your computer with you as the sun expands to destroy the Earth. That assumes you haven't left the Earth already, because in a billion years it's predicted that the Earth has a billion years left for complex life to thrive. After that, the sun will become so hot from compression of gas in the core that it'll be too hot for photosynthesis to continue, and all complex of life would be dead. So, yeah. Another similar problem would be with Sudoku puzzles. So, you're given a puzzle like this, and the goal is to fill in all the blanks such that every row has a unique digit 1 through 9. Every row has a unique digit 1 through 9. Every column has a unique digit 1 through 9. And all of these 3x3 boxes have a unique digit 1 through 9. So I see a 1 here, and a 1... So I see a 1 here, and a 1 here. That means that I cannot put a 1 here, but I could put it in these two squares, because there's already a 1 here. So that would narrow my possibilities to having a 1 here and a 1 here. And that's the only place I could ever have a 1. But that's actually not what I'm talking about. It's not solving a Sudoku puzzle, but rather, what is the fewest number of given digits, as they're called, to solve? What is the fewest number of given digits you can have on a Sudoku puzzle, and have it be solved in such a way that you will always get a unique result? If you had any fewer than that, you would end up with a Sudoku puzzle that had more than one solution. So, again, also the naive way to do this is to write down every possible Sudoku puzzle and start solving each one until you get a situation where you had so few digits you couldn't solve it without getting more than one answer. Yeah, so those two examples, God's number and what is the fewest number of given digits you can have on a Sudoku puzzle. Brute force alone is not enough to solve these kinds of things. Well, brute force will help, but it would also help if you had some way of reducing the amount of work you had to do. On a Rubik's Cube like this, you can exploit some of the symmetries that a cube has to reduce the number of cases you had to go through. Similar things applied with finding the fewest number of given digits you can have on a Sudoku puzzle. That number turns out to be 17. You can have as few as 17 given digits on a Sudoku puzzle and have it be solvable with only one unique solution. Yeah. So yeah, those are so when we apply those symmetries, we reduce the number of possible board configurations that we have to go through, and then it might be reduced enough that we can just brute force it the rest of the way. The quest of finding the tallest cactus in Minecraft kind of worked in a similar workflow, actually. So I'll just summarize what happened, and then you can watch a video for yourself. In Minecraft, there are 281 trillion possible seeds that can generate a world. That's 2 to the 48th power. That is a lot. Not as much as the possible states on a Rubik's Cube, and also not as much as the number of possible Sudoku puzzles. But anyway, the seed finding would scan a Minecraft world for any instances where a cactus spawned on top of another cactus. If you play Minecraft and you ever see a 4-block tall cactus in the world, that is because 2 different cactuses of the same size spawned on the same location, and they stack together to form a taller cactus. So that is one way we can find. So I'm basically summarizing the entire video. It started off with scanning Minecraft seeds to find tall cactuses. Then it got reversed so that we would find seeds that generate a world that had tall cactuses. All of this also applies to another related Minecraft-related endeavor, and it is to find the seed for an image that was only 128 by 128 pixels. The search for the seed that generated this specific feature was thought to be an impossible task, but just a few years ago, it was completed. They found the seed for a 128 by 128 image. Here's how it's done. There's a lot that goes into Minecraft world generation, but once you find where in the world such a feature would have generated in, you can can reverse engineer the world generation system, and I'm just gonna say right now, it would take forever to just brute force the 281 trillion possible Minecraft seeds to find this one image. So instead, narrow it down through. You would narrow down the search space from 281 trillion to a couple million, and once you have it narrowed down that way, then it becomes way easier to brute force. If you want to know more about the technical details about that example, look up Sal C1's video on pack.png. It is an interesting trilogy. Okay, so what does this mean for us when we're just looking at the seven of Eratosthenes? This is the matrix multiplication thing. What I want is the sieve itself. So eventually what I want you to do is to write your own sieve of Eratosthenes program. I've shown this code already, but I've also talked about I had to make a few changes to make it run faster. If you can find ways to make a program run faster, that speed up starts to become more significant when we try to run the same program for... We're gonna be running the sieve of Eratosthenes to as large of a search max as we can. And similarly, I would encourage you to run the Pythagorean triples finder to as large of a search max as you can, too. But for now, eventually I'm going to want you to write your own sieve of Eratosthenes that looks more or less like this. How I wrote it is, I have a for loop that initializes an entire vector full of numbers from 1 to the search max. To those numbers. I have it declared here as a vector full of zeros, but I needed a separate for loop to give it all the numbers. And then I enter a nested for loop that I've explained several times already. But before any of that, we have to do start equals high resolution clock :now. We do that, we fill the array, we fill the vector full of numbers, and then we say that 1 is a non-prime number, and then we enter the nested for loop. At the end of all that, we say stop equals high resolution clock :now. We find the difference in execution, we find the difference in time between start and stop, and that's our execution time. And here I have it printed out. So if I'm to run this, it's gonna take a while, because I have it searching up to like a really big number. That took 18 seconds to find prime numbers up to, what is this, 100 million? And then it printed out the prime numbers. It printed out a sample because to print out all the prime numbers would just take forever. We just want the execution time, really. Eventually, what we're going to do is we're going to make something... We're going to make a table of execution times. And again, we're only considering execution times of running the program on our own computers. It's not like computer versus computer. It's really thread count versus thread count versus, it's like thread count versus different thread count versus search max versus different search max, all on the same computer, so we only have two variables to worry about. How many threads do we have, and what is our search max? And remember, the ultimate goal of parallel computation is really to try to solve these really big problems in a more reasonable amount of time. That example of going through all 43 quintillion possible Rubik's Cube scramblings, we could somehow have 43 quintillion processes on one computer or a whole network of computers, and each process tries to solve one of these. One of the possible 43 quintillion scrambled Rubik's Cubes. That would be horrible to do because I don't think... Do we even have enough computing resources in the world to concurrently run 43 quintillion processes? If we can reduce that number by considering the symmetries of a cube, and then run a brute force algorithm that does this divide. So let me just summarize how God's number was found. And you can look at JPerm's video to see whether I was explaining it correctly. So, a team of programmers got together and basically brute forced the whole thing. But they did so by reducing that 42 quintillion number by recognizing that this thing is symmetric. It's got all sorts of symmetries. They reduced that, and then they ran the whole program on a distributed system with the aid of like Google's computers. And it still took them a while to find out that God's number was 20, but at least it took a more reasonable amount of time than like 5 billion plus years. Anyway, I think it's worthwhile to watch the video to see how, not only how they found God's number, but how it was specifically done. How it was specifically done to not only reduce the number of possible states to go through, but how it was eventually distributed on a cluster to finally solve the problem. Anyway, when we are looking at execution times for the sum of Eratosthenes, what I would want you to do is you would run the program for however many threads your computer has. My computer has, once again, an 8-core, 16-thread CPU, so I can run up to 16 threads by default. So in my case, I would run the program for varying core counts, varying thread counts. From 1, 2, 4, 8, and 16. I'm going by powers of 2 because it's easier that way. And that's one column. No, and that's one variable. The other one is search max. So we could look for prime numbers up to 100, 1000, 1 million, and 100 million. So we would end up with a table that looks something like this. We can have more numbers in between, by the way. This is just an example. I'll give more explicit instructions on how to do this. But what we would need to do is, for each combination of thread count and search max, we would have to run the program at least 10 times, or as much as we can. run the program a few times, get an average execution time, and then we can write those averages all in a table. And then we can use that data to plot out line graphs showing what the execution times look like compared to one another. I have the class set up so that we meet on Monday to discuss. I have this class set up so we have our Q&As on Monday. So if you want to know how to write up an entire table in Excel and then make the line graphs for it, I can show you how to do that. But eventually you would produce, at the very least, that table of execution times. Yeah, at the very least you'd have a table of execution times. But if you want to go a little above and beyond, we can make a table that looks like this. So here's a table of different thread counts and different search maximums. So here I have the average execution times in microseconds, and then I had to translate that data into a series of line graphs here. So what this says here, let's consider this first row, which is searching for prime numbers up to 1000. What it actually says is if searching for primes up to 1000 constituted 100% execution time, then if we're to use 2 threads, we end up with an execution time that's more than double from before. With 4 threads, it goes up to nearly triple. With 8 threads, it's over 600. It's over 600%, and so on and so forth. And that's why the line here just goes up. In comparison to larger search maxes, we get some speed up. The execution time does go down, but it may go... Hold on. I think I got it backwards. Okay, no, yeah, I was right the first time. So, in the case where we had 1000 as a search max, so searching for prime numbers up to 1000, no matter how many threads we threw at the problem, we would get worse and worse execution times, and that's because of all the context switching that has to happen between so many threads. No, it's not just the context switching, it's just that you have to divide the work. There's all sorts of overhead that happens when you divide a problem like this. But if you go up to larger and larger search maxes, then you start to see a benefit, and then that benefit starts to taper off. So that's what this table says. And that's what this line graph is saying. So, for a given search max, we want to see whether adding more threads to the problem decreases the execution time, and if that is worthwhile. Whether such an increase is worthwhile. So, here for an extremely small search max, yeah, it executed in like 100 microseconds, which is what? If you're running this only like a few times, then that's insignificant. Those time savings, if they exist, and they don't, they're insignificant. Even in the case where we had the program running for 10 times longer than the 1 thread case, it's still, oops, it's still nothing compared to the 10 million case. And yeah, we can throw some number of threads. We can keep throwing threads at the problem to see whether it speeds up more and more. And then we reach diminishing returns. This starts to go into what's known as Amdahl's law, which is a law that describes the maximum number. It describes the maximum speed up given a program with a specific number of cores and a specific proportion of parallel and non-parallel code. Next week I'll probably include a little presentation about that, but as an example, if you had a program where like you only had 10% parallelizable code and then the other 90% is not parallelizable, in the most optimistic case, you can throw as many threads as you can to that parallelizable code, and in the limit, in theory, that 10% will shrink down to nothing. In practice, it doesn't work like that, but pretend that it does. It would make no difference to the fact that the other 90% of the code cannot be parallelized. So you'd be limited. So your speedup would be limited to how much. In that case, your speedup would be limited to how much non-parallel code you had in proportion to the parallel code you did have. If we however flipped it around, so now we had 90% parallel code and 10% non-parallel code, now you would be limited by however many threads you have available. So if you had 2 threads, you would cut down that 90% down to 45. And so now your program runs in, what? A little over half the time as it was previously. Amdahl's law gives you a speed up as a multiplier, so you have to divide percentages to get the entire thing. But again, I'll show you what that looks like next week. For now, what I want you to do alongside your matrix multiplication program is to start writing out the sum of arithmetics and try to get some execution times if you can. We can also. So with that, I'm going to end the video now. I'll let you go do your assignments. If you have any questions, let me know. When we meet up on Monday, if you want to have any questions answered in person, and then we can start looking more at Amdahl's law and more on the sum of arithmetics, how we can speed it up, how we are supposed to get this data collection process going. We'll look more about what to do with the sieve, data collection, all that. For now, just focus on your next assignment, which is the matrix multiplication program, and yeah, we'll continue on with further matters next week, and I guess I'll see you then. Thank you.